Hello everyone, welcome back to another class on regeneration biology. And in today's class, we will learn about the future implications of organ culture in patient care, which basically we will discuss how the future or how we are going to take ahead the organ culture in a regeneration context or a patient care context. Organ culture, we have seen it by now, why and how we know, but still we will do a recap. Organ culture offers significant future implications for patient care, potentially revolutionizing organ transplantation and disease research in general. So, creating a lab grown organ and using that organ to culture to study various diseases can address the reasons of how the disease manifests in the host, and also you will also know how it is responding. If you are putting a new organ, how it is going to respond in the host, and also we will understand better about the organ shortage issues, and also how can we get rid of the rejection, minimize the rejection risks, and allow for personalized medicine. So what are the factors that we can add up into the cultured organ that can minimize or mimic more of a humanized organ? So these are all the future angles. Furthermore, the organ culture can provide a more clinically relevant model for studying disease mechanisms and drug efficacy in traditional cell culture means, or whatever we can learn from a traditional cell culture, we can learn a much more when you are creating an organ and studying about the organ. So not that every time the organ which you are culturing you must use for transplantation. You can study the organ's behavior in vitro as well. If you look into an update in US, what is by this is the statistics from 2020 from a published paper, as it is mentioned here. The most needed organs on a transplant wait list and their respective percentages in 2020 has been given in A, and in B the number of individuals on the wait list and the number of transplantations performed from 1991 till 2019. That means roughly around 30 years. That is what has been shown here. And in C bottom, the number of transplants performed in 2019 organized by based on whichever organ you are talking about. So you can see here the majority of the trouble is in the wait list is the kidney transplant 83, and 11% is for liver. And then you can see heart, lung, and other organs, because these are all the main organs that are in demand. Because they fall apart much easily. And if you look into donor donor availability and also the transplantation, if you look in this panel, you can see transplanted is going to be more or less same. Hardly there is any change from 91 till 2019. A marginal increase is there, and the waiting list has gone exponentially. You can see here the waiting list has gone way too high. So the gap from the demand to supply, the gap is very high. It has widened the gap. And the transplants performed in 2019 alone is around 23,400 transplantation in US alone. They have done it. And if you see for kidney that much, and for liver it is around 8,000, you can see, so on and so forth. So just in 2019 alone, you can see what is the number of transplantation. That number is huge. Pancreas, intestine, lung, etc. So it says it is an alarmingly large number of requirement is increasing. So addressing the organ donor shortage, how do we address it? Lab grown organs cultivated from the patient's own cells could eliminate the need for a donor organ. You don't need to wait for a donor, you can make it, solving the critical shortage problem. Being genetically identical, because it is made from your own cells, these organs would significantly reduce the risk of rejection, and the major hurdle of the current transplantation is the risk of rejection itself. So you can get rid of that. So the personalized medicine and improved outcome. So the current scenario, it is going into such a stage that you don't want to be a burden on others. So you have your own cells and you produce it, you have money, or you have the opportunity to make an organ and you transplant it. In vitro organs can be customized to individual genetic profiles, improving the transplantation or transplant success rates and long-term outcome. Because since it is your own organ, it will stay back for a longer time. This approach aligns with the trend towards personalized medicine, tailoring treatment and each patient based on the each patient's specific needs. So since your own organ is being made, you don't need to be in immunosuppressants, hence you will not have any more complexity because of the immunosuppressants. So enhance the disease research and drug development. So the organ culture provides a more accurate model for studying disease mechanisms and drug effects than traditional cell culture. That is why although in cell culture you can make cells expanded and you transplant into the diseased organ, if you can make the organ itself, all of them will be new, and the trouble that is facing the patient still in that residual organ will not be there at all. You can damage the organ, you replace it with a full-fledged one, fully functional organ, then this tissue culture based production can be avoided, especially when you are transplanting the cells. You can transplant the organ itself. Researchers can use diseased organs, even those removed during surgery, to investigate the causes of disease and identify potential treatments. So you can also take an organ and then take the cells from it and you culture it and make a new organ and see that, does this cells hold clue on why the disease occurred at all. So there are multiple angles where you can, and then in vitro you can treat with the different drugs and see, which drug is helping, which drug is contributing to the repair, etc. And overcoming the limitations of existing methods. The traditional cell cultures, like production of cells, can lose key functions over time, making them less reliable models, while organ culture preserves the integrity of cells and tissues within their natural environment. Because when the cell is a three-dimensional, of course credit goes to the ECM, and then it will be more homely than when you make them into a two-dimensional flat surface. The organ on a chip technology, which we have discussed in the past, a form of organ culture, allows for studying fluid dynamics, nutrient support and drug gradients, offering a more physiological approach. Organ culture is much closer to the functioning of the organ than just a tissue culture. So if you look into the future directions, there are multiple options are there for organ culture. Bioprinting, 3D bioprinting technology we have discussed in the past is paving the way for creating complex organ structures, potentially leading to the fabrication of functional organs itself. And then comes the stem cell therapy. So stem cells can regenerate damaged tissues and organs, offering potential alternative to organ transplantation. Say myocardial infarction, you have created a fibrosis, and because of which heart is not contracting. You can get rid of these fibroid tissues and colonize them with cardiomyocytes or stem cells that is capable of differentiating into cardiomyocytes. Now the fibroid tissue is having a functional heart muscles. So these are all the approaches of stem cell therapy. Then comes to the regenerative medicine. Research into regenerative medicine, including organ regeneration, could lead to developing new therapies for organ failure. We can understand the reasons and situations through which an organ is failing. Let us see what are the challenges and considerations to be kept in mind. One is functionality, ensuring that lab-grown organs function properly and can be scaled up for clinical use remains very challenging, because like there is a saying, the cow in the book will not eat grass. So although it is an ideal organ you made it, if it is not been integrated functionally, it's not because of your immune rejection, due to its structure is not made properly, so that the neuronal connection, the blood vascular connection is not ideally linked, then that organ will not have a future. And the regulatory network. Establishing clear regulatory frameworks for the development and use of bioprinted and other engineered organs is very, very important. Otherwise, you can end up in getting in a lot of trouble. So the regulatory networks has to be established precisely so that there will not be any legal or non-legal or medico-legal issues come. And then comes last the ethical consideration. Ethical debates surrounding lab grown organs and their potential implications for patient care need to be addressed. A rich man decides, oh, my liver is not up to the mark. Liver has no problem. He's thinking, no, I want to live for another 50 more years. So my liver, let me get it fixed. Oh, my kidney is old. So let me get my kidney fixed. Oh, my lungs are very old. They have got some disease. So let me get that fixed. Let me replace my individual organs, all of which are all vulnerable, which is going to affect my longevity. A rich man decides then whether giving him a longer lifespan is ethical or not. So these are all the angles that will come into picture. Approaches to engineering the whole organ. Let us see, there are two major approaches are there. One is a top-down approach, another is bottom-up approach. So let us see them in detail. There are two major approaches, like I told you. One is the top-down construction and bottom-up construction. So the concept of top-down engineering is to develop scaffolds that cells can grow and form functional tissues after their growth on that. And macroscopic or even whole organ scaffolds are seeded with one or many cell types where a combination of scaffold remodeling and self-assembly leads to the formation of complex 3D tissue or the whole organ itself. In contrast, what we see is bottom-up engineering utilizes the smallest component elements of tissue such as collagen molecules as building blocks and combines them to assemble a larger construct. So you make pieces and then you assemble, or you already have a large scale and then you allow the cells to colonize on it. Similar to the erecting a building by adding one brick at a time, the bottom-up engineering methods are designed to control and organize the interaction of cells with each other and their surroundings. This is how they work. And using stem cell engineering, it is very much possible to utilize a single building block, human pluripotent cells, HPSCs, to engineer construct such that the organoids, and organ-specific functional tissue through the bottom-up approach. So top-down and bottom-up approach both can come hand in hand when you are thinking about engineering a whole organ. So the comparison of top-down and bottom-up whole organ engineering strategies are mentioned here. Top-down approach, here we have got the cells and then you have the scaffolds. So stem cells or differentiated cells, or you have got a biologic or synthetic scaffolds. You bring them together, seeding, repopulation and self-organization into complex tissues. That is what you are seeing in a top-down approach. In bottom-up approach, what you are seeing, additive manufacturing. That is basically a 3D printing where you use the cells or biomolecules or substrates and you put them together and you make a complex biological structure which is meant for making a replication. So both are done in a manner to benefit the patient, but the approach, the strategy is different. So if you look further, if you want to conclude the way in which how the regeneration or the regenerative medicine or the organ culture is evolving, we know significant interest has been made in whole organ engineering globally. Tissue engineering and regenerative medicine over the past few decades, it has grown exponentially high in a alarming or in a very much promising or like a in a logarithmic scale it has grown, because there are dedicated institutes, there are dedicated programs have evolved to meet the demand of organs. So this has been especially true because end stage organ failure continues to be a leading cause of morbidity and mortality around the world. Maybe because of your eating habit, maybe because of your living environment, maybe because of your stressful condition, organ failures or humans' organs started failing more often than before. in the recent era. So, orthotopic organ transplantation is currently the only curative treatment option that is available for patients diagnosed with end-stage organ failure. As of now, there is no other alternative is available. However, significant advances in bioengineering of the whole organ constructions continue to advance rapidly, giving hope to those waiting for a transplantation. So if you look further, the key technological advancements have supported whole organ engineering over the past few decades. These include number one, the methods of whole organ decellularization and recellularization, which we discussed, how you take a pig's heart and get rid of the cells and use only the matrix and colonize it. You can revisit back. And then three-dimensional bioprinting, where you can make the organ itself, and advanced stem cell technologies, and fourth, the ability to genetically modify tissues and cells. These advancements give hope that organ engineering will become a commercial reality in the next decade. So that is what the scientists believe, or the medical science believe. However, we must understand that several barriers exist to the commercialization to become a success, are still the major obstacles that need to be systematically addressed. Engineering whole organ construct with adequate cell populations is a significant technical barrier, as it is the currently highly challenging to create an engineered organ with a homogeneous cell density close to the high cell density that native organs possess. We must understand each organ is very tiny in the embryonic stage when new organism is developing. Then the cells are proliferating, and they are not proliferating like a balloon. They are proliferating like some of them are dying, some of them are growing, again apoptosis, again proliferation. So there is a tug of war exists, because of which with available less space, when you allow an organ to grow, they are quite dense. But when you are culturing them in vitro, you will not be able to provide that environment. Like when my kidney is growing, it is having pressure from the intestine, pressure from your body muscles and body fluids, liver on top, lungs on side. These pressure are not there when you are culturing, because of which the cells will remain loose. So this is one challenge which organ culture faces. To address this barrier, stem cell research must be developed to improve cell invasion and adhesion of organ constructs. We cannot tell cell come close, come close. So you have to apply some pressure so that it can be dense enough. In addition to improving the density of cells incorporated into engineered whole organs, the diversity of cells used must also be improved to better mimic the cell diversity found in the native organ tissue, what is present in the actual organ. So through the whole organ decell and recell approach, decellularization and recellularization approach, and the cell bioprinting approach have demonstrated the ability to incorporate multiple cell types into engineered organ constructs. Now it is possible that you can incorporate multiple cell types into the cultured organ. This is often to replicate but a single part of an organ's function rather than replicating the entirety of the organ's function. It becomes little difficult. A part you can deal with it. Also, though the variety of approaches to stem cell culture and differentiation, whole organ recellularization and decellularization, bioprinting, and genetic modification techniques being developed is conducive for research purposes. Standardization is vital for clinical implementation. That is another angle which you should. It's not that you can, one patient came and you just made an organ. Okay, I don't know whether it will work or not. I made an organ, you take it. If it worked, good for you. Otherwise, not good for you. It can't happen that way. One has to standardize. And remember, each patient is unique. So we cannot standardize in X person and expect the same result in Y person. So it is remaining a challenging situation. Standardization necessitates comparing various methods in comprehensive studies to identify the safest and most effective approaches to engineering whole organs. So, as demonstrated by multiple studies performed by different research groups, this is the fact which we get it from various other research studies. As an ultimate goal of whole organ engineering, it is the clinical translation and transplantation. These standardized protocols must undergo strict regulatory examination. So, the regulatory pathways plays a very major role. The regulatory pathways are an additional challenge that is facing the utilization of engineered whole organs as viable transplants and are principal among the non-technical barriers to the commercial implementation, which basically means regulatory pathways should not hold in between the use of cultured organ to the patient. So that has to be more conducive to the patient community. This is an important challenge, although it may sound very technical, important challenge, as the regulatory pathways ensure the novel medical technologies can only be used commercially if they can properly demonstrate safety with all potential risks and their respective likelihood of occurring being documented. One simple example, you made a fantastic drug for cancer and it cures every non-cancer. However, that drug, when you want to solubilize it, that solubilizing agent is slightly toxic. It is not going to kill you. It is slightly toxic. You will not get FDA approval or any other agency's approval. It is not going to kill you. Maybe more toxins are there through your food. But the moment that particular solvent is coming under a toxin or not so friendly molecule, then you cannot. Like urea is produced by your body. It is a toxin. So, but you cannot use urea as a solvent for consuming. You are not going to die because you had small quantities of it, because it is there in your body. But same logic applies. These regulations has to come in an idealistic scenario. So as a result, as a manufacturing said organs and in another challenge outside the developing transplantable whole organ technology. The current approaches for engineering whole organs involve processes with low production volumes and no indication of the ability to maintain consistent quality on a commercial scale. So as a result, the current methods of whole organ engineering would not be able to reach to make a difference in reducing the number of individuals who die from end stage organ failure. Technology is there, but it is not powerful enough or sufficient enough to reach into don't worry, there is a solution. Partial solution, some people are getting benefited, but not to reduce the number significantly. The patient death significantly is not been achieved yet. As such, developing novel manufacturing techniques in parallel with the ongoing whole organ engineering research is a necessity. So, despite the field of whole organ engineering being quite new, much attention has been focused on it. So, it is, and the relevant technologies such as stem cells have been developed to advance whole organ engineering. So, ideally, one has to find out whether transplanting few stem cells is beneficial for this patient, or you need to transplant an entire organoid or an entire organ itself. So this has to be dealt with. You cannot say, and again, like I mentioned, each patient is different. So in one patient, you put few cells and he or she did not survive. It can raise questions. So there was an option of putting the organoid, whole organ itself, but instead this doctor put only cells, which was not powerful enough. These are all the challenges which the implementation stage, it can get into a serious trouble. Though there are many barriers to the clinical implementation of engineered organ, the critical need for the replacement for the allogenic organ transplantation makes the whole organ engineering research vital in overcoming these barriers. So what we understand that the replacement of an allogenic organ through the transplantation, it makes the engineering of the whole organ very, very important and it's vital in overcoming any of these barriers. So ideally, we can conclude by saying that the technology is out there. You can make the organ and you can transplant to the patient, and in some patients it works effectively and efficiently, and there is no serious trouble which stops them from getting these benefits. However, the long term goal, once you put the organ, just because it was not autologous, it is not made from their cell, or maybe the humanization of that pig heart or a kidney or a liver did not work the way it should have worked, all will come back to a serious question to the medical science or the research community. That is why when you are implementing any of this technology into a commercial scale, experimental level, it is working. Terminally ill patients, people are doing because doctors will say yes, they are not going to survive, they are not going to make it. Then you are not experimenting, at least you are trying. Okay, this patient is not going to be alive, so why not we try necessitate their further movement, or push their biology with the help of this transplanted organ that is available, and that has been done. But it has not reached a stage one can get across a counter and say that, okay, hey, I want an organ, so let me get it transplanted. So this is what I had to explain about this future prospects of the organ culture. However, I would like to say an overview about this whole course in maybe next 2 or 3 minutes. So this course was designed to elicit interest in the research community a lot. That means student community and also research community can understand that there is a field called regeneration biology exists, and there is a huge potential, and the future, the demand for regeneration biology or the experts in regeneration biology is going to go sky high. And in many countries, developed countries have moved a lot ahead. There are dedicated regeneration biology institutes, and there are many dedicated programs exist to nurture and favor the regeneration biology. But in our country, we are still catching it up, although we have got some institutes dedicated for regeneration biology research, such as INSTEM Bangalore. But the potential for a country like India is much, much high, and the research community also should develop along with the demand. That is why the courses like this regeneration biology becomes more attractive and more fascinating. So in general, the best way to learn about the regeneration biology is to learn from those organisms who can regenerate. So the question is very simple. If you have a damaged organ, why it prevailed? Like if your skin is peeled off, it is not going to be an open wound forever. After 1 week it heals. Why not your damaged organ? Whatsoever the reason, why don't it fix it? And in some animals they do that. They don't suffer that, if their organ is failed, it's not that, rest of the life is with that failure. It doesn't survive. Like fishes and frogs are examples which we have studied. And why such a mechanism don't exist in animals like mammals or humans? That is the big question. So in this whole course, we were trying to understand that how do we deal with, or how do we learn from these various models of organisms, and how they behave or how they interact with the environment in a damaged condition, and how they fix the damage in a given amount of time. What is the trading it does, whether to go for a wound healing versus a regeneration, what decided, or who is the decisive factor. So these are all the things which we learned from this course. And I would also ask you to read several textbooks and also review articles to enhance your knowledge, because this field has got a huge potential and no one should hold back there. Even though some of you may not be an actively studying student, some of you may be taking this course maybe as a part-time job, but try to kindle this information or knowledge what you gained by expanding, so that it can be helpful for your family and other friends, family, relatives, etc. So I would very strongly suggest that you should enhance your knowledge by reading more and more about the latest development in the field, because that is good for the country and good for the mankind and the whole planet. Okay, so I hope all of you had a nice training from this course, and those who waited for this until up to this last lecture, I really appreciate your patience and tenacity, and all the best for all of you. Thank you.